You guys, today I'll be taking you to applied electricity EE151, and today we'll be looking at circuit and network theorems. So today we want to look at resistors in series, resistors in parallel, and how to calculate the effective resistance. So without wasting much time, I think let's jump in. So I know in class already they might have already explained to you when they say resistors are in series and when they say resistors are in parallel. So basically, we say resistors are in series when the same current flows through them. So let's say if from this resistor, let's say if 10 amps is flowing through this circuit, then that means the 10 amps will flow through this one, and the same 10 amps will also flow through R2. So that is why they say both of these resistors are in circuit, meaning the same current, this 10 amps will continue to flow through the whole of this circuit and back, so making them in series. And another condition is that they said there is no junction between them, as already they explained in class that a junction is a point where current splits or divide. So junction, there's no junction between them. So basically, this is what I also use simply in a layman's term sometimes to identify resistors in series. So I always ask myself, let's say if current starts to flow from here, this current starts to flow from, so when it gets here, is it that is there any option for it to pass? No, there's no any option. It just have only one path to take. So meaning they are in series. Since there's just only one path, meaning when the current from here it gets here, it just moves all the way back, and there's just only one path for it. So basically, sometimes that is also one way you can easily use to detect whether they are in series aside the definitions. So it's just there's just only one path for current to flow, so making it in series. So let's say practically in your rooms, in rooms mostly they connect this thing, light bulbs in series. So some of you might be asking yourself, where will I be applying this? So light bulbs are wired in series, so that's why sometimes when you switch on, it will turn on about 4 lights or 2 lights. So that is the concept of series resistance. So let's move on forward. Looking at the second circuit, you see that we have R1 here, R2, and R3. I want to look at this circuit. Although there is a junction here, we observe that there is a junction, and the definition for a junction was that is where a junction is a point where current splits or divides. So let's say if we have current flowing from here, let's name it I1. So if we have current flowing from here, I1, so when I1 gets to this junction, it will split up. So some will come here, some will come here. So none of these resistors are in series, sorry. None of these resistors in this circuit are in series, so are none of them are in series. So this was just an example I wanted you to understand. So what is next? I wanted you to take you through the practicals. How do we calculate resistors in series? So resistors in series can be found, so we can say total resistance, which we normally call it RT, should be equals to the sum. It's typically the sum of all the resistors in series, since it's just they are in series and it's just one closed path. So for the figure 1, we say the total resistance equals to R1 plus R2. So basically, we have a general formula that we use to calculate resistors in series and resistors in parallel. So this is the formula which is used to calculate resistors in series and resistors in parallel. So you just sum all of them just like this. R1, they summed R1. So RT here is equals to R1, R2 plus R3 plus dot 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 2. It's just the sum to infinity. If there are even 1000 resistors and all of them are in series, you just add them up. Okay, so let us move to a simulation. I have a simulation here that will really show us what the resistors that are in series and how the current flows. So, but just as I was saying, you see that the current started flowing from this voltage source, and from this voltage source, it started moving to this resistor. Then it moved to this resistor. then it got to this branch, then it came back all the way back, meaning there's no path for it here. The current is just moving in a straight line and back. The same current, if let's say 10 amps is flowing through this one, the same 10 amps will flow through this and all the way back. So that is how basically it is. So I think from here, if I want us to take an example so that we really understand, in case there's a question, we'll know how to handle it. So this is a problem. Problem one. They said, what is the total resistance in the circuit below? So as we said, note, I forgot to add one thing. All the units are in ohms. Resistance is measured in ohms, and voltage is measured in volts, and um, current is measured in amps. So these are in ohms. I forgot to add them. So now we know the formula already. It is equals to the sum of resistors. So now we say our RT here is equals to our R1 plus R2 plus dot 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 up to Rn. So now here, how do you solve this question? We have our RT here is equals to our 20 plus the 11. This and this are in series. This resistor is in series with this, and it's in series with this and this and this. These two are, everything here is in series, so we simply just add them up. So we have 20 plus 11 plus 50 plus 18 plus 17. So when we do the math, we will get 116 ohms. So please always make sure to write the units. If you are working for voltage, you know the answer should be in volt. When you are calculating resistance, when you finish, you don't leave the units, because when you leave the units out, if it is a theory question, they will mark you wrong, because they will give you not get the full mark. Yeah. So if the question is like maybe two and you write and you leave the units, maybe you will not do it, you will not get the full mark. And maybe if it's MCQ, if it is MCQ, they can set it like uh, since the answer is 116 ohm, they can have 116 volt, 116 amp, 116 ohm, just to confuse people. So the questions are really tricky. The course is not difficult. So I want us to move on to parallel and parallel resistors. So okay, so now moving to parallel resistors. Resistors are said to be in parallel when the voltage across them is the same. That's the basic definition for resistors in parallel. So I want to show you some ways that you can easily identify resistors in parallel, and so that you will not waste time. So let's say they give you a circuit like this. This is how I easily identify my resistors in parallel. So what I do is that, let me say they've given me R1 and R2, and I don't really know. Let's say I don't even know the definition that resistors are said to be in parallel when the voltage across them is the same. Let's assume that I don't know that, and I want to really find out which of these resistors are in parallel. So R1, we have R1 here. Sorry, we have R1 here and we have R2 here. So I want to consider, let's consider this figure first. I want to consider which of them are in parallel. I want to check whether they are in parallel. So basically what I do is that if I start from one terminal, from this point, if I start from one terminal and I'm able to circle the two resistors from one point to the other and back without meeting any third element, that means the resistors are in parallel. So if I'm able to move from this point all over to this point, to this side and back, and I only meet the two elements, the two resistors that I'm considering that they are in parallel, that means those resistors are in parallel. And since this R1 and R2 are in parallel, I can just denote it as R1 is in parallel with R2. So in some books, this is how you will see it when resistors are in parallel. So further, if we are going on in calculation, when I identify resistors in parallel, this is how I'll write it. So in parallel, we just denote them as this with those two bars. So even in exams, when you do it like that, they will tell you to prove your answers. When you do it like this, they will know that yes, when they are marking, maybe if they want to give you extra point, fine. So for this one too, we'll look at this. So from here, I'll be able to move from here all the way to this resistor, down, all the way to this place, down, back to here, meaning R1 and R2 are also in parallel, because I'm able to move, the cycling is working. I'm able to move this from this to this. I didn't encounter any third element. I only encountered the two resistors that I'm considering that they are in parallel. So I can also say from here that R1 is in parallel with R2 in this diagram. So moving on forward, we have a general formula in calculating resistors in parallel. And so since the resistors are in parallel, we have a formula which is 1 over RT. I know that they proved this formula with you in class, and the proving isn't really important here. You should know how to use the formula, that's all. So if you want to know how to prove it too, fine. So we can simplify this as RT is equals to R1 R2 all over R1 plus R2. So this formula can become like this. So this is the total resistance formula, the resistance formula for resistors in parallel. So let's say if there's a third resistor, I can add it, R3 here plus R3. So that is how it is. So I'll take a simulation for us to see how it really works. So so this is the formula, as I was saying. This is the formula you will need to do your calculations. So so with the simulation, I think I want to simulate resistors in parallel. So with resistors in parallel, let's look at this. So from here, we realize that the voltage, this is the voltage source. When it delivers the current, when it gets to this node, just from the definition of the node, we know that a node is a point where current splits or divide. So at this point, the current, some splits and some are going to this side, some are going to this side. Then it comes down. So one trick I also want to give it to you guys is that to easily detect whether resistors are in parallel or not, always ask yourself whenever there is a current flowing from the source. Let's say the current starts from here. When it gets to this node, ask yourself, does it have a choice or it has no choice? If it has a choice to choose a direction, that means basically it tells you that there is a parallel there. There's some parallel happening somewhere. Because at this point, if it was in series, it wouldn't have had a choice. It would have just all moved, all the current would have moved and all to one side and all the way back. But at this point, it has a choice either to go to the left or to go to the right. So that is why they say at a junction is a point where current splits or divides. So moving on forward, I think at this side too, you come to see that the current here, it gets here, then splits. So let us use our trick, the trick I showed you, to easily see whether we can identify the parallel networks or not. So here when we come, we realize that when we want to circle from this node, we can circle to this resistor all the way back here, then we move back here. We didn't meet any third element, meaning this and this are in parallel. Then we can also circle from all the way here. We move back here. They are also in parallel. This one and this one are also in parallel. Then we can also move from here all the way here, down, then back, telling you that this and this are in parallel. So basically that is the analogy for parallel and parallel circuits. So we'll move on to one of the next important concepts, so that when we understand those concepts, we'll be able to solve questions. So we will now look at some of the important concepts we need to be able to analyze circuits. So I think basically applied electricity really centers around these concepts. So something like short circuits, open circuit, and things. So now we are going to deal with short circuit, and I really want you people to understand the short circuit well, because if you don't really understand short circuit well, you might not be able to, you might have an issue solving questions. So what is a short circuit? A short circuit has practically zero resistance. So in class, uh, there might be other definitions, but we can just say practically has uh, zero resistance. So when we say something is a short circuit, when a circuit is a short circuit, what makes it a short circuit? So a circuit is a short circuit. That means there's no resistance on that line. So basically, when there's a short circuit, when the current sees a short circuit, it just moves. So let's say for this circuit like this, let's say voltage, this is the voltage. So since there's a short circuit at between B and G, there's a short circuit between B and G, so the current will just move all the way to, it will move, and when it gets to this node, and from our previous discussions, we said a node is a point where current splits or divide. But when it gets to this node, instead of it splitting, since there's a short circuit, there's no resistance here. Basically, let's say the resistance here is basically like zero, it's less. So we can't say it's zero, but it's less. Since there's no resistance here, it will just decide to take this path, then this path, all the way back to the voltage source. So one trick I want you guys to use in identifying a short circuit is this. You see, whenever there's a short circuit, that means there's no resistance. Listen to this. So there's no resistance there, and basically there's a free path. It's basically like, let's say you are coming to campus, and the queue to the shuttle, there are so many people on the queue just fighting for shuttle. They realize that on the route the road is less busy, so you do, because you don't want to struggle with those things, you just pass through the place that there are not a lot of people there. Then you just get a chance and enter. I don't know if it's making sense, but yeah, I hope you understand. Like, current doesn't want to go through stress. That's how current is. The current doesn't want stress, so basically it always just wants a free path so that it can easily move and come back. So the concept of the short circuits, when we say short circuit, that means, let's say basically we are saying zero resistance, meaning our resistance there is equals to zero. And you know, from Ohm's law, V is equals to IR. So with the V being equals to IR, it gives rise to two things. That means the voltage in short circuit should be equals to zero, if you agree with me, because we'll have a value for I. Let's say if they give us a value for I, even no matter if I is 1000 multiplied by 0, our answer becomes 0. So basically, in a short circuit, the voltage is basically 0 volts. And I think I will do another video where I will do a simulation showing you why in a short circuit the distance, the voltage is 0. So let's say if you want to analyze this circuit right now, since we've identified that there is a short circuit in this uh, this circuit, basically the circuit will now become like this. If you're analyzing this circuit, it will now become like this, because this is how the circuit will now look like, because the whole of these resistors, if you're analyzing them, the whole of this circuit will not be considered, because when the current gets to this side, instead of it splitting, there's a free path here. I will not split, I'll just pass through and come back. And one thing is that current through a short circuit is very large. It's very large. So it's like infinity, like it's very large. So that is one thing we need to know. So going on, I think when we take an example, you understand. So let's say this is our second example. You see that there's a short circuit here. So let's say current starts to flow from here. When it gets here, it comes to meet this node. And from our definition, we said a node is where current is placed. So when it gets here, current will not split, because at this node, you realize that there's a free path here. It's just a free path, like it doesn't want pressure. So it just comes all the way back to this. So basically, this side, let me use a different color to denote it. So this side of the circuit would not be considered in our analysis, this side. So let's say if I'm going to redraw this circuit again, so this the part of the circuit that will be considered in our analysis would be this R1, only R1. So meaning both R2, R4, R3, all of them have been short circuited because there's no current that will flow through them. It will not allow current to flow through, because when the current gets here, it just diverts back all the way back, and it comes back. There's a closed path. Because there's a closed path, the current can flow. So it doesn't really have to go through the stress of the other resistors. I hope you are getting it. So there's a simulation. I have a simulation that I want to let us look through, and it will really help us understand. Just to take an animation and look at and appreciate the concept of the short circuit. So as I said earlier, I told you that on this circuit, the whole of R2, R4, R3, they will not be considered in our analysis because there's a short circuit here. When the current starts from here, it moves to R1. Then since there's a free path at this point, it just moves back and back. And one thing you have to know is that current can never be lost. Current is never lost. That is one thing, because if 10 ohms is leaving this side, that means when you add everything back, it should be 10 ohms. That is how it is. So current can never be lost. So all the way back. So I want to use this simulation to explain it better. So we have a circuit here. So you see that it started moving. You see that the yellow arrows going is the current, shows the current. You see that nothing really moves on these two resistors. That means they've been short circuited. Look at it. It moves all the way here to here and back, because there's nothing going through them. There's nothing going, because you see, if there was current passing through, you would have seen this yellow lines moving down, but it tells you that no current is going through them, nothing. They've been short circuited and they are just there. So if you are analyzing the circuit, you only consider this resistor, because this and this have been short circuited. They've been short circuited because ideally when the current gets here, it should split. But the current realized that there's resistance here, which is a very high value, even if it was not even a high value crowd. Since there's a free path, let's just listen to it has like nearly zero resistance, because let's look at here. From here, this side, there's no resistor here. So even if I was going somewhere, this road is crowded, then I will just decide to come and take the road that is not crowded. Then I'll come back. No stress. You're making your life simple. So that is how current is. So basically, I hope this one helps you to really understand the concept. So, because you see that this one and this one, there's nothing flowing through it. So that's it for short circuits. Then we'll move to the second concept, which is open circuit. We'll be dealing with the next thing on our line is open circuit. So with open circuit, is a branch that has infinite resistance. So what it means is that, like, let's say there's a broken path. That's basically, in a layman's term, there's a broken path. Let's say there's a broken path where the circuit is not complete. So meaning current can't flow through it. That's what, when they say something is open circuit, that's why you should just come. There's a broken path, so meaning there's some breakage there that is obstructing the flow of current. So let's say there's some, let's say, a bridge. If there's a bridge somewhere linking two communities and the bridge collapses, meaning you can't access the other community again. So there's a broken path. So in electricity, we call something like that is an open circuit. So this is the open circuit concept. So with the open circuit, this is how we denote it, open circuit it. So with this open circuit, what you realize is that when current also starts to flow from here, it moves here and it gets here. You know, current is very smart. That's one thing I want you guys to keep in mind. It's very smart. It's not like it wouldn't come and take this path, and when it gets here, you say, oh, it's open circuited, then, oh, I'm going back. Because as I said earlier, we said current can never be lost. Current cannot be lost. That's one thing. So when the current starts flowing, then it gets here and it detects, it will automatically, before it will even get here, it will detect that there is an open circuit. Since there's an open circuit here, it will just divert all the current back here, pass through here, then back. So basically, in the open circuit, when you are analyzing this circuit, we only consider this. We can also redraw this. So if you want to redraw this to analyze the circuit well, you can just redraw it like this. Then, sorry, I know my resistance is not nice, but let's just manage. So we can just say it's only this resistor that will be considered when we want to talk about open circuit. So I have a simulation again to show you how it is. So basically, with that, you see, the current flows from here then all the way back. No stress. So there is no stress in itself from here all the way back. From here all the way back. It doesn't even come here. You see that it doesn't come there because there's an open path. Because when it comes here, the current will be lost, and current can never be lost. So it has to be complete. There's a closed path. Current flows in a closed loop. So that is how it is for open circuit and closed circuit. I hope you guys, you really understand it. Yeah, so thank you very much. And I think from here on, we are now well equipped enough to take on serious questions and answer them. So meaning if you understand this concept well, we can now take exam questions and past exam questions, and we'll try to see how we can answer them. So now our next topic online is what we call effective resistance. So basically when we say you find the effective resistance, so we simply identify the resistors that are in series in a circuit. Then the next thing, we add those that are in series together. Then we also identify those that are in parallel. Then we add them together. Then we finally add both the series and parallel together. So I'll take an example, then use it to explain for us to really understand. So find the total resistance in the circuit below. So just as I showed you my principle, they say we should find the total resistance in the circuit below. So what do we do? First of all, there are three resistors. So there's 1 ohm, 2 ohm, and 3 ohm. What do we see? Let's say, let me try to analyze this circuit in so many different ways for you to understand. So let me say, if I don't really know the definitions for parallel and series. So we realize that there is a voltage source here, there is 1 ohm resistor here, there is 1 ohm resistor here. So let me say R1 ohm and 2 ohm, are they in parallel or are they in series? I don't know, but let's use the method I use, the circling method. So when I start from here, I meet this resistor, then I meet the second resistor, I meet the third element, then meaning they are not in series. I've made a third element, meaning they are not in parallel. Since I've made a third element, I can't say 1 and 2 are in parallel. So that is not good. That is not going to work here. So let me now consider another set of resistors. Are 2 and 3 in parallel? Then let's use our circling method. So I move it from here to here and back here. I realized that I didn't meet any third element. So meaning the 2 and 3 are in parallel. So what do we do next? From our formulas we use, we said resistors in parallel is equals to 1 over R1 plus 1 over R2, and we further on simplify this. So we can say so first of all resolve this resistors, so which is the R here is equals to R1, which is this, which is the 2, which is 2 times the 3 all over 2 plus the 3. Then we'll get an answer. So after getting that answer, we redraw the circuit again. So after redrawing the circuit, we can now see that the circuit will now become very, very simple. So we'll get 1.2, which is also equal to 6 over 5. 6 over 5 ohm, which is also equals to 1.2 ohm for the resistors in parallel. Then we redraw the circuit again. So after redrawing the circuit, this is what you come and get. So after resolving them, this is what I get. So I've resolved this and this. So what do I realize? I realized that after resolving this, after adding these two things, they were in parallel, so I added them up. We see that this one and this one, they are in series because the same current will flow through them. See, when the current comes, it doesn't have an option, it just takes only one path. The same current will flow through them. So I simply add my 6.5 to 1. So finally, I can now say the R total, RT, which is equals to the 1 plus 6 over 5, which is equals to which is equals to 2.2 ohms. 2.2 ohms. I hope we are okay. So with this, we've now been able to calculate the effective resistance or the total resistance. Sometimes they'll tell you effective resistance or the total resistance. So this is just as I denoted. So as we move on, you get to understand. So we'll take another example to really understand what we are doing. So with the next example, they said find the effective resistance of the circuit below. So what do we do? To find the effective resistance, we have to identify the resistors in parallel and identify the resistors in series. Then we add them up. Then we add them up to get our final answer. So let's take this resistor. Let's consider this resistor. Let's consider this resistor. If I circle this resistor, we are identifying parallel resistors. If I circle this and this, they are in parallel because 2 and 2 are in parallel. So what do we do? So we say R parallel is equals to 2 times 2 all over 2 plus 2. So after doing this, what do we get? 2 times 2 all over 2 plus 2, which is equals to 1, which is 1 ohm. So we have to redraw the circuit again. That's the best thing I will tell you. Always redraw the circuit after resolving it. So that means you've added this and this and they've become one. It now becomes one resistor. So you can just basically clean one. Then you bring it. So what do we do here now? We now redraw the circuit. So after redrawing the circuit, we'll come and realize that this is our next circuit. So if this is our next circuit, what do we see? All what we see is that this and this are in series. The whole of this circuit are in series. So we add the 1. So the R series, so we can say R series here is equals to the 2 times 2. R series here is equals to the 1 plus 1, which is equals to 2 ohms. So we now have our R total is equals to RT is equals to we found the R series. So we just add this one and this one, and this one is series. So we say R parallel plus R series should be equals to 1 plus 1, which is equals to 2 ohms. So that is our final answer. So this is the solution here. I have my solution here. So mostly this is how you find your resistor in series and resistor in parallel. So we'll take another example. We'll move on for so find the total resistance of the circuit below. So this is a complex question, but it's nothing too big. So first of all, this is the complex circuit they've given to us, and they are saying we should find the total resistance. So what do? We first of all find the resistors in parallel and resistors in series. So we realize that the 4 and 6 are in parallel. So first of all resolve them. So after resolving them, we'll get an answer. Then we also resolve them. That is how it is. So we say 4 and 6 are in parallel. So 4, 6 are in parallel. Then after resolving them, we'll get a circuit like this. We'll come and get a circuit like this. We'll come and get a circuit like this. But we also realize that after solving them, this and this are in series. No, let me do it right, because since you don't really, I want to show you all the step all the way down there. So after resolving them, we have 4 in parallel with 6 here. Then we have 2. Then we have 3. So what do we observe? We observe that this and this are in series. So we can redraw the circuit again. So redrawing the circuit becomes, I always like, since to understand things better, mostly I prefer that you redraw the circuit. So as you continue to redraw the circuit, you will really get to know what you are really doing. So basically it becomes 4 in parallel with 6 plus all plus 2 in series, because it's in series with this, then 3. So what do we observe? We come to also observe that this and this are in parallel again. So our final then becomes this way. It becomes our RT, which is the 4 by 6. 4 times which is 4 times 6 all over 4 plus 6 all over 4 plus 6 plus 2 all parallel to 3. So when we do our mathematics here, we'll come and get 22 over 5 parallel 3. So finally we get our RT here is equals to 22 over 5 times 3 all over 22 over 5 plus 3. And finally we come and get 66 over 37. So this becomes our final answer, 4, which is equals to, if I want, I can leave it in decimal place, which is 1.784 1.783 1.7838 ohm. So in applied electricity, I always advise that you leave your answer in 4 decimal places so that you'll be safe, because if you go and leave it in 1 decimal place, it doesn't really help. So that is it for this question. I hope we are okay. So this is the solution. I have the solution down here. Let me just display it so that you can see the process I did. So as I stated to you already, when resistors are in parallel, we denote them like that. We just denote it like that. So 4 and 6 were in parallel, so we say 4 is in parallel with 6. So those two arrows are showing you that they are in parallel. And when you just see plus 2, that is just addition to 2. So that's what it really means. So now we'll move to another problem, which this is our second problem. They are saying we should find the effective resistance of the circuit below. So we realize that the 50 ohm, this 50 ohm, and this 50 ohm are in series. So we first of all add this 50 and this 50 to get 100. So it becomes 50 plus 50, which gives us 100 ohms. So after getting this, we have to redraw our circuit again, and redrawing our circuit, we end up with another circuit like this. This is 20, this is 20, and this is now 100. So what do we realize? We realize that this 20 and this 100 are in parallel. So we use our formula for resistors in parallel, which is 20 times 100 all over 20 plus 100, which gives us 16.67 ohms. So we now find the total resistance. So our RT here, let's redraw the circuit so that we'll really see what is happening here. So this becomes our 16.67, 20 ohms. So our RT is equals to the 20 plus 16.67, so which is equals to 36.67 ohms. Problem 3. Find the effective resistance of the circuit below. So what do we see here? We see that this 6 and this 2, they are in series. This 6 and this 6 are also in series. But when we combine all of them, when we combine this and this, you will get 12. We combine this and this, we get 8. We get 8. So we can say, we can redraw the circuit again. So I always encourage you to redraw the circuit, because it really helps. So we have 8 here, then we have 12 here, then we have another one here. So what happens? We also observe that this and this are in parallel, because we can circle them, the two of them, without meeting any third element. We can circle them without meeting any third element. So we have to also resolve them. So after resolving, we see that they are in series. So resolving, we have 8 here times 12 all over 8 here. 8 all over 8 all over 8 plus 12. So our 8 times 12 all over 8 plus 12 is equals to 4.8 ohm. So what do? We redraw our circuit again. So we now have this, then back, where this now becomes our 4.8. This, what was the value of this? It was 2, here was 6. So here is 2, here is 6. So now basically our RT, our total resistance, is equals to, we simply add the 4.8 plus the 2 plus the 6. So we add 4.8 plus 2 plus 6, which is equals to 12.8 ohms. So our final resistance is equals to 12.8 ohms. So you see we started from this complex circuit, we simplified it to this, then we simplified it to this. So basically it's just addition, subtraction. That's what we are doing here. We are not doing, after you are able to analyze the circuit. Okay, so now let's solve problem 4, and the question states, what is the effective resistance of the circuit below? All resistances are in ohms. So this one here is 3, in case you are not seeing it well. Let me write it well for you. So we'll realize that 4 and 6 are in parallel. So 4, 6 are in parallel. So let us resolve that. So 4 times 6 all over 4 plus 6, so which is equals to 5.4 ohm. So after resolving it this way, I always tell you that you should always redraw your circuit so that you really understand how things are going. So we've redrawn our circuit. We have our 5.4 here. Then what do you realize? We realize that again, this 4 and this 5.4 are in parallel again. So we'll resolve them as well. So we have 4 times 5.4 all over 4 plus 5.4, so which is equals to 2.3 ohms. So after doing this, what do? As usual, we have to redraw our circuit again, then we'll know how to analyze it from here. So this is now how our circuit look like. So what do we observe here again? Also observe that this one and the 2.3 are in series. So we add them up, which becomes 1 plus 2, 1 plus 2.3, so which is equals to 3.3 ohms. So what do? We now redraw our circuit, our final circuit again, to really know what is happening. Then our final circuit is redrawn. So realize that this 3 and this 3.3, the 3.3, they are all in parallel. So also resolve that to get our final answer. So it becomes 3.3 times 3.3 all divided by 3.3 plus 3.3. So our final answer becomes 1.65 ohms. So this is simply how we solve this circuit, although it started as a complex circuit, but we ended up solving it to become a very simple circuit that we can all analyze. So we can say our RT here is equals to 1.65 ohms. This is our answer over here. Okay, so now let us solve problem 5. Problem 5 says find the total resistance and the total current in the circuit below. So this is the circuit that is given to us over here. So our circuit is given to us here, but when we observe the circuit critically, we realize that there's a short circuit somewhere. So we realize that the 3.5, the 5 ohm and the 7 ohm are short circuited because when current starts to flow from this 25 source, it gets here, is placed, it gets to this junction, is placed. But when it gets to this junction, it realizes that there are resistances here, but there's a free path here for it to pass and come back. So it just decides to take this free path all the way back. So basically, when we are analyzing the circuit, this 3.5, 5 ohms and 7 ohms wouldn't be added. So we'll redraw the circuit to this. So our new circuit that we'll consider in our analysis is this: the 4 ohm resistor, 1 ohm, 2 ohm and 3 ohm. So what do we realize from this circuit? We realize that the 2 ohm and the 3 ohm are in parallel. So let's use the approach I told you earlier. So we can circle from here to here to here to here to here without meeting any third element. We only meet all the two resistors that we are considering that they are in parallel, hence they are in parallel. So let us resolve that. So what do we say? 2 times 3 all over 2 plus 3, which is equals to which is equals to 6 over 5. So which is equals to 6 over 5. Let me write it well. Which is equals to 6 over 5 ohms. So after doing that, we will now redraw our circuit again, and after redrawing our circuit, what do we realize? We realize that this 4 ohm and this 6 over 5 we just found are in parallel. Let's do our drawing. So we can start from here. We pass through this resistor, come and pass through the second resistor, all the way back to the first resistor without meeting any third element, meaning they are in parallel. So we also use our parallel for that. So it now becomes 4 times 6 over 5 all over 4 plus 6 over 5, which gives us 12 over 13. 12 over 13. Then we'll redraw our circuit again. So our new circuit now becomes this 1 ohm, in series with this 12 over 13 we just found. So meaning if current starts to flow from here, all the current will flow, the same amount of current will flow through the whole resistor. So all the resistors in the circuit. So we now do our calculation. So we can now say we know that they are in series, so we say 1 plus 12 over 13. So we can say our RT, which is our R total, is equals to 1 plus 12 over 13. Then we get our answer as 25 over 13, which now becomes our final answer. So our final answer now becomes this 25 over 13. And the second question they asked us was that they said we should find the total current in the circuit. And from Ohm's law, we know that V here is equals to IR, comma R here is given to us as 25 over 13, and V is given to us as 25 in the circuit. So basically we just need to find current, and we can find current by doing change of subject, which is equals to the V over R. So now it's equals to 25 all divided by 25 over 13. So we have our current as 13 amps. So as I said earlier, always write your units. Whatever you are calculating for, if you are calculating for current, leave it in the right unit. Current is measured in amps. So what does this current mean when we come back to the circuit? So it means this voltage source, this 25 voltage source, delivers 13 amps of current to both the 1 ohm resistor and the 12 over 13 resistor. So meaning 13 amp current flows through this whole circuit. That's what it means over here. So from here I'll be moving to our next concept, which we'll take some examples then and we are good to go. So our next concept is called the current division rule. So with the current division rule, I'm sure they might have shown you how to prove the formulas and everything, but I am not going to do that here. I'm just going to explain it to you and how we use the formulas to solve questions. So basically, this is the before you can use this rule, you have to always resolve your circuit to look something similar like this. So you see that the current divider rule, it has two resistors in parallel and it has a voltage source. So you realize that this is the total current flowing through the circuit. This is the total current flowing through the circuit, and when it gets to this junction, it's placed and some come down here and some also come down here. So that is why if we now want, you might be asking yourself, why do we use the current division rule? So if you want to find the current through this resistor or the current through this resistor, you know that we said resistors in series, the same current flows through them, but for resistors in parallel, the same voltage flows through them. So here we know that different current now flows through this resistor, so we want to find the different current so that we know that the amount of current that flows through them. That is basically why we use the current division rule. We just always want to find the current. So one thing I want you to also look at, also study the direction of the arrows. So these arrows, all the arrow here is pointing downwards. The arrow here is pointing here to this side. When it gets here, it's placed. So this arrow point downwards. Then when it gets here, it's also pointing downwards. So let's say if this arrow was pointing upwards, there would have been something we would do. So basically the current division rule, the rule states that to find the current in I1, you simply, since you are looking for the current in I1, you simply take the opposite resistor, the resistor that is opposite to I1. So which resistor is opposite to I1? Is R2. So that you take it as your denominator and you divide it by the sum of all the resistors. So you divide it by the sum of R1 plus R2, then you multiply it by the total current. That is what it simply means. So this is what I'm saying. So the first one says to find the total the current I1, we simply say I1 is equals to the total current here. This is the total current multiplying by the opposite resistor. See that this is the opposite resistor. So finding I1. To find I1, you multiply it by the opposite resistor. Then you divide it by the sum of the resistors, which is R1 plus R2. Then you have found I1. So to find I22, it's basically the same thing. You also multiply it by the opposite. So now we are finding I2. So to find I2, they are saying we should multiply it by the opposite. Which one is opposite to I2? Is R1. So we should multiply the total current by R1. So it now becomes R1 times the total current all over the sum R1 plus R2. So basically, to find the current for the current flowing through I2 R2, the second resistor. So these are the two formulas that you need to know how to derive them and use them in your calculations when they need arise. But let's look at something very quick here, a quick thing here. So what we do is that, let's say if the direction of this current, let's say this arrow was pointing upwards, I2 was pointing upwards, something would have happened. You see that already this current here is coming inside, it's going clockwise, and if this side was going anti-clockwise, meaning it was going opposite to the direction of this current, so meaning we would have just added, the formula would have changed small, so I2 would have become minus negative, because it's going against the flow of current, is going in the anti-clockwise direction. R2 would have become like this. We'll just negate it, because if, let's say, the arrow was pointing up, I'll take an example, then we'll really understand it from there. Okay. So we are taking problem 6. So problem 6 says find the values of I1 and I2. So from our previous example, we said to find the value of, so we are going to find I1. We said to find I1, to find I1, to find I1, we simply take the opposite resistor, and which resistor is opposite to I1 is 2. So our I1 here is equals to 2. Then we multiply it by the total current, and the total current is 10. Then we divide it by the sum of the resistances. So we sum these resistances, then it becomes 3. It becomes 3 plus 2, which is now equals to 4 amps. So basically, that is just what I do. This is the formula. So you see, basically equals to R2. This is R2, the second resistor, divided by the sum multiplied by the current. So we'll get 4 amp, which gives us this. And they said we should also find I2. To find I2, we equally use we are finding I2. So we come and use the opposite resistor, which resistor is opposite to R2. So I2 here is equals to 3 times 10 all over 3 plus 2, which is equals to 6 ampere. But let's not forget, let's look at the arrow here. The current is pointing to inside, but the I2 is going against the flow of the current. So basically we negate the formula. We just negate the formula here, just as I explained earlier. So our answer becomes minus 6 amp. Then this is the formula we use, then we get I2. So I think we should be good now. Then I'll take our last example for this series, then we are good to go. So our last example, problem 7. So with problem 7, they said we should find the value of I1 in the circuit. And how can we find the value of I1 in the circuit? Realize that they've given us the total current, they've given us I1, but we realize that their resistances are 3 here instead of 2, because we can't use the current division law. If we want to use the current division law, we have to resolve some of the resistance in order for it to suit the equivalent diagram that they gave it to us. You see that the current division rule,
there were only two diagrams, so we have to only use two resistors. There were only two resistors, so here the resistors are three, so we have to resolve them. So what do we realize? We realize that these two and these two are in parallel, so we can easily resolve them. 2 times 2 all over 2 plus 2, which is equals to 1. Then we have to redraw our circuit again. So we've now redrawn our circuit, and what do we see? We see that the 3 ohm is now our R1 and the 1 ohm is now our R2, and they said we should find I1. So I1, how do we find I1? I1, just to find I1, we are finding I1. I1 is the opposite resistor multiplied by the total current, which is 1 times 10 all over the sum of the resistors, which is 3 plus 1. So it's now equals to 2. Our resistance will now be equals to 2.5. Our current is now equals to 2.5 amps, and we are done. So this is basically how we find our current, then using current division rule. So please, in case you have any more questions or there's anything you don't understand, you can reach me on this number 0240 752417. So for those outside the country is +233. That's my country code. So you can kindly reach me on this number with any questions you want us to solve together. Then kindly like my videos, subscribe, and leave your comments there. Leaving your comments there will let me know the kind of questions you want me to tackle. If you don't understand, just type it there. I'll check through, and the kind of videos you want me to upload. It will really go a long way to help. And kindly remember to share if you really think this video really helped you to really understand a lot of your concept. Kindly share it with your classmates and your coursework, to share it in your class groups so that others can also benefit, because applied electricity is very simple. If you really know the tricks and understand the concepts well, you can easily blow, and it's a 3 credit hour course. So if you really perform well in this course, at least it will give you a good start, to give you a good CWA. So have a nice day. See you in our next video. Bye.